previously we showed that we could prove divisibility using proof by induction or sometimes logic, and now we're going to show how modular arithmetic can help us show divisibility as well. So we want to show that if a whole bunch of digits represent the value x in base 10, then x is congruent to the sum of its digits mod 9. Well, if this is true, then that implies that 9 is a divisor of x minus this quantity, so minus the sum of its digits. And that goes back to our definition of congruent. So we can rewrite x since it's a number in base 10, and this was written as a hint for us. So if we're going to write x in base 10, I know that x is going to be equivalent to 10 to the n times x to the n. Sorry, not x to the n, x sub n. So here I can rewrite my x value as 10 to the n x sub n plus 10 to the n minus 1 x sub n minus 1 plus all the way down until I hit 10 to the 0 x to the 0. And so now I'm going to subtract off these terms if I rearrange them to line up. Now, what I'll find is that I'm going to have 10 to the n minus 1 x to the n's. So here I'm just looking at my right-hand side here. So 10 to the n minus 1 x sub n's plus 10 to the n minus 1 x sub n minus 1's plus. Now I'm going to have x naught minus x naught, so that's going to end in 0. My term before that is going to be 10 to the 1 minus 1 x's. And then we end with 0, of course. So notice that this 10 to the n is going to be a 1 with n zeros at the end. I subtract 1, I'm going to end up with a number that's a bunch of 9s. In fact, I'll have n of them times x sub n plus, same thing, n minus 1 9s, x sub n minus 1, all the way down to 9x. Of course, I can factor out a 9 from this, so this is equal to some 9k. Therefore, this is true, that 9 is a divisor of this quantity. Therefore, x is equivalent to the sum of its digits mod 9.